Hey everyone, welcome back to the channel Code with AKJ. Today is day 33 of solving LeetCode 75 challenge series, and today we are going to start a new topic, that is binary tree DFS. So if you're new to the channel, please make sure you hit that subscribe button and turn on notifications so that you never miss an update from this channel. So let's get started with our first question, that is maximum depth of binary tree. So the problem statement says, given the root of a binary tree, return its maximum depth. A binary tree's maximum depth is the number of nodes along the longest path from the root node down to the farthest leaf node. So why is this problem important? So it's a fundamental tree traversal problem, and its concept is widely used in graph traversal, recursion, and dynamic programming as well. So let's understand what is maximum depth of a binary tree with these three examples. So I have represented here three different binary trees. So the maximum depth is nothing but the number of nodes present from root to its farthest leaf. So in this given binary tree, we have three different leaves, that is 9, 15, and 7. And the maximum depth is the number of nodes present from a particular node to its leaf. So for this given leaf node 9, we have two number of nodes from root, so the depth for this particular leaf is 2. And from 3 to 15 we have three number of nodes, so the depth here is 3. And from 3 to its 7 leaf node we have three number of nodes, so the depth is 3. So maximum depth of this given binary tree would be the maximum of 2 comma 3 comma 3. So for this example, the maximum depth of the binary tree would be 3. So coming to this given binary tree, we have only one leaf node. So the number of nodes present from root to its farthest leaf is the only one leaf node, that is 2. Have two number of nodes. So the maximum depth of this given binary tree would be 2. So coming to this binary tree, we have three leaf nodes. So the distance from 1 to 4 is 3. That is, we have three number of nodes from root to this particular leaf node. And we have three number of nodes from 1 to 5. And we have four number of nodes from 1 to 7. So the maximum depth of this given binary tree would be the maximum of these three values, that is 4. So the maximum depth of this given binary tree would be 4. So this is what problem statement says. We have to find the maximum depth of a binary tree, that is the number of nodes present from a root to its farthest leaf. So let's start with our initial approach. So in this approach, we'll traverse all nodes and calculate the depth of each subtree recursively. We'll take the maximum of left and right subtree depths and we'll add 1, as we need to include the root itself. So this particular method will ensure that we visit all the nodes. So let's quickly understand our brute force approach. So we'll start with the root. We'll give a recursive call to its left subtree and right subtree, and we'll calculate the depths of these left subtree and right subtree. And when we try to return from that particular call, we'll try to add 1 to it, as we are including the root itself. So 3 gives a recursive call to its left subtree, that is 9, and 3 also gives a right recursive call to its right subtree, that is 20. So when 3 gives a left recursive call to 9, 9 again gives a left recursive call to its left and right. So the left and right of 9 is null. So when the node is null, we'll return 0. So the left of 9 returns 0 and right of 9 returns 0. And when we try to return from 9 call, we'll add 1 to it as the maximum of left subtree depth and right subtree depth plus 1. From 9 call, it will go back to 3, returning 1 as an answer. In the same way, it gives right recursive call to 20, and again 20 gives a left recursive call to left subtree and its right subtree. Again 15 gives a recursive call to its left subtree and right subtree. So since they both are null, they will return 0. From 15, it will return 1 plus max of 0 comma 0, which would be 1. So the left recursive call of 20 would give 1 as an answer. And when it comes to the right recursive call, again 7 gives a left recursive call and right recursive call. They both return 0. And returning back to 20 would give us 1 plus max of 0 comma 0, that is 1. So for the node 20, the left recursive call and right recursive call gives 1 1 as an answer. So after returning back to 3, we would add 1 to it, as we need to include the 20 value as well. So 1 plus max of 1 comma 1 would be 2. So for this given node, we'll calculate the max depth, that is 1 plus max of 1 comma 2. So max of 1 comma 2 would be 2. So 1 plus 2 is 3. So in this way, with the help of recursive call, we'll visit each and every node and we'll calculate its left subtree and right subtree max depths, and we'll try to return it by adding 1 to it. And in this way, we'll able to find the max depth of a given binary tree. So let's quickly go through these two examples as well. So one gives a left recursive call and right recursive call. So the left recursive call is null since the node is 0. So it would return 0. And when it gives a right recursive call to 2, it again gives a left recursive call and right recursive call. They both return 0 and 2 returns 1 as an right recursive answer. So for this given one, the maximum depth would be max 1 plus max of 0 comma 1, that is 2. So for this given example, 2 would be the max depth of a binary tree. So coming to this example again, it gives left recursive call, right recursive call. 2 gives to 4, 4 gives to its left node and right node, so both are null, they would return 0. 4 gives 1 as an answer to its 2, and 5 gives 1 as an answer to 2, and 2 returns 2 as an answer. So for the left recursive call, the 2 would be a answer, and 3 gives call to 6, 6 gives calls to 7, 7 returns 1 to 6, and 6 returns 2, 2 to 3, and 3 returns 3 to 1. And finally, the max depth would be 1 plus max of 2 comma 3, that is 1 plus 3, which gives us 4. So for this given binary tree, 4 would be our max depth of a binary tree. So this would be the idea of brute force approach, where we are using where we are recursively visiting all the nodes and trying to find the max depth of its left tree and right tree. So the time complexity of this approach would be O of n, as we are visiting each and every node here, and space complexity here would be O of depth of a tree, that is the height of the tree. So let's quickly code our approach. So in our approach, we were giving left call, that is finding the left depth by calling our function again, sending root left, and we were also calling the right depth by sending root right. And finally, when we were trying to return, we were adding 1 to the max of left depth value and right depth value. So here our base case would be that if we found a null node, that is if root is equals to null, we'll return 0. So let's quickly run this code. It's working, so let's submit. As you can see, this gives us successful submission. So the time complexity of this approach would be O of n, as we are visiting each node once, and space complexity would be O of height of tree, that is because of recursive stack depth. So here I have written a binary tree. So if we closely observe this given binary tree, to find the maximum depth of a binary tree, we can say that the number of levels present in a given binary tree is equals to the maximum depth of a given binary tree. So instead of recursively calling all the nodes and calculating its depth, we can directly calculate the number of levels present in this given binary tree to find our maximum depth. So in BFS, we'll try to move level wise using queue, and we'll increment the count variable after every level is being processed. So the number of levels present in our binary tree would give us maximum depth of a binary tree. So let's quickly dry run with this given example and understand how BFS works. So we'll take a queue. So initially we'll push 3 here. So after popping this 3 from this given queue, we'll try to push its left and right values, that is 9 and 20. And we'll take again the front value here. Since its left and right values are null, we'll move on to the next node, that is 20. So we'll move 20 from the queue and we'll push its left value and right value. And again, coming to the next iteration, we'll take 15. We'll pop this 15 from the queue. We'll push its left and right values, that is null. So we'll again move to the next node, that is we'll take the 7 value. We'll push its left and right. So they both are null. So since the queue is empty, we'll stop our processing. So here we can see for every level of nodes we have been processing, we are popping the root and we are pushing its left and right child values. So every time we are popping the root value and pushing its left and right values, we will increment a count variable, that is the next level is being processed right now. So this was for the first level, this was for the second level, and this was for the third level. So we'll use a count variable or the depth variable, which would be initially 0, and for every time a level is being processed inside a queue, we'll increment our count variable until or unless our queue becomes empty. So in this case, since the queue is empty at the last iteration, the count was 3, so the maximum depth of this given binary tree is 3. So in this approach, the time complexity would be O of n, as we are visiting each and every node here, and space complexity here would be O of width of the binary tree, as we are using a queue which contains almost a maximum width of this given binary tree. So now that we have seen both the approaches, both DFS and BFS, where the DFS time complexity was O of n and space complexity was O of height, and whereas in BFS the time complexity is O of n and space complexity is O of width of the binary tree. In this given problem statement, DFS is more optimal and reliable, especially when trees are deep and unbalanced. Coming to the BFS, it may give TLE and can be inefficient for deep or wider trees. For example, there's a tree which is wider and has large number of nodes, so our queue would contain a large number of nodes inside it. Processing of those number of nodes would give us time limit exceeded. So even though BFS is a valid approach, DFS is more optimal and reliable for a problem like this, especially when trees are deep or unbalanced. So let's quickly go through our time complexity and space complexity analysis. So we have observed both the approaches, both BFS and DFS. So DFS takes O of n time complexity and O of height as space complexity, whereas in BFS the time complexity was O of n and space complexity was O of max width of binary tree. So in this problem, we would prefer DFS as the tree might be deeper or unbalanced, whereas in BFS it may give TLE for wider trees. So we'll not prefer BFS for this kind of problem statement. So that's it for today, guys. We have covered both the approaches, DFS and BFS. So let me know in the comments which approach you use more often. If you haven't already, hit that subscribe button and stay tuned for more awesome coding content. I'll see you in the next video. Thank you.